Good morning, everyone. Bom dia a todos. Welcome to today's webinar, Amália Towards a Multimodal LLM for European Portuguese, part of the LLM webinar series organized by NCC Slovakia in cooperation with NCC Portugal under the EuroCC project. My name is Božidara Pellegrini. I'm from NCC Slovakia and I will be your host today. Before we begin, please note that this session is being recorded. The recording will be available afterwards on our YouTube channel and the NCC Slovakia website, so you can rewatch it or share it with your colleagues who couldn't join us live. To ensure a good experience and high quality of the recording, all microphones will remain muted during the presentation. During the Q&A session, if you would like to speak, please raise your hand and your microphone will be unmuted individually. And you're always welcome to write all of your questions in the chat. Today's webinar introduces Amália, Portugal's national large language model designed to bring the richness of European Portuguese into the era of multimodal artificial intelligence, combining text, speech, image, and video understanding. Now, let me briefly present our speaker. Professor João Magalhães is co-director of the CMU Portugal program and head of the Multimodal Systems Group at Nova Links, Nova University Lisbon. His research focuses on vision language models, multimodal learning, and AI systems for semantic multimedia. He holds a PhD from Imperial College London and is one of the leading figures in Portugal's AI and digital innovation ecosystem. So please, Professor Magalhães, the floor is yours.
Thank you. Thank you very much for the kind introduction, and good morning, everyone. I will be today presenting some of the work that is being done in Amália, and given the audience, so I've prepared the presentation in the context of supercomputers and how this is trained in large-scale supercomputers. So I think this will be of interest for everyone, so both from the field of NLP and from the field of distributed computing. So the Amália is a national LLM, and it's in the context of, sorry, let me change the slide. Okay, so this is in the context of European innovation strategy, which was somehow outlined the innovation strategy in the Draghi report, in the sense that we must profoundly focus our collective efforts on closing the innovation gap with the US and China, which are the leaders in this area, and we definitely need to close the gap. And basically, European AI gigafactories and all the work that is being done in AI, it can contribute to improve healthcare. Like we can see here all the improvements, all the benefits that we can get, and this has been shown in the past that Europe can do it, like in CERN and in many other areas. For example, in the CPUs areas where you have ARM processors. So this is something that is possible. We know that it's doable, and in the meantime, many countries followed this initiative, where you have multiple LLMs being developed in different countries, and this has the benefit of getting more data that covers the European cultural traits. We improve the skills of local researchers and companies, so we improve innovation by doing this, and instead of just being the end users of these LLMs. And so this is a big benefit for Europe. And to make this happen, the ingredients that we need to put in place are basically three. So we need computing power, of course. We need the Calian supercomputer, the Mare Nostrum supercomputer, other supercomputers that are available. We need data. We need data, which we have Portuguese data available in the National Library, in theses, education materials that we have in FCT and Arquivo, so the Portuguese Web Archive, which is a local version of the Internet Web Archive. And then obviously we need the team that knows the algorithms and knows how to run and how to implement these AI systems, which here it's Nova, Técnico, Universidade de Coimbra, Universidade do Minho, Porto, Beira Interior, and Universidade de Évora. So this project is being coordinated by myself and by my colleague André Martins from Técnico, and we are building the core of the model, which will then be used in downstream tasks by other colleagues. In terms of the computational infrastructure, so we have been basically using Mare Nostrum and some local clusters just to do the normal data processing, which is more convenient in our local clusters. But then when we want to scale up the simulations, then we go to Mare Nostrum. Okay, so we use the GPU partition in Mare Nostrum, and we run simulations up to 120 to 250 GPUs per simulation. And so in terms of algorithms, so we have this idea of generative large language models. And what I wanted to outline today and to present today is to, so the outline of today's presentation is to go through the training steps of the LLM, of an LLM. And we are following basically everything that I'm presenting here today. There are other details, of course, but the key insight is here. And if you have any questions about how we deploy some of these simulations in Mare Nostrum, please just drop a question in the chat and I will try to answer. So basically a generative large language model, it's one type of large language model which has the capacity of generating answers, of generating responses. You have large language models which are so-called encoders. They do not generate answers, but generative LLMs, they get a user request and they can generate a given response. And so for now, let's just assume that this is not that it's an isolated box without internet access, and everything that the model replies, the model has to know by default because it has no access to the outside world. Okay. And so how is an LLM trained? So the LLM is trained in three phases. The first phase is the pre-training, the second is the instruction tuning, and the third is the preference learning. In the pre-training phase, we collect large amounts of data, we filter by quality, we make sure that it's GDPR compliant, we have trillions of tokens, but the training task is really something very, very simple, which is language modeling. Okay, so we are predicting only the next word. That's the key task. And this is where most of the computational resources go into. It's in this phase, okay? And so some people argue that, okay, language modeling, it's something really simple. These models don't know a lot. They are only predicting the next word. It's true. It's only predicting the next word. But it's not actually true that the model is just learning the next word, learning how to predict the next word. And so let me go through now some step-by-step discussion of what language modeling means and the implications of it. So language modeling objective is, so you have this idea of, you have this sentence, Lisbon is famous for its, and now we can get a probability for each word that we have in our vocabulary. Okay, so we have vocabularies with, let's say, 100,000 words. Okay, and words here, so it's actually a token. It's not exactly a word, but it's a token. That's why we have more than 100,000 entries in our vocabulary. And so basically, we have this sentence: Lisbon is famous for its, and I can complete it in many different ways. There are more than one correct ways, but some are more likely than others, okay? For example, Lisbon is famous for its weather. I would agree with that, but okay, these mountains, it's not so famous for its mountains, but imagine you have here gastronomy or something like that, okay? And then you have a very high probability in the words that are more likely, and in the words that are less likely, you have lower probabilities. And in the word that it's really not likely at all, for example, Lisbon is not famous for its zucchini, or or aardvark, so it's almost zero. Okay, so this is a really simple task, but you can actually learn a lot. Let's see what the model learns by doing this very simple task. So it learns how to do grammar. Okay, when I have sentences like this, in my free time, I like to, and this phrasal structures requires a verb to close the sentence and not a noun. And so the model this way will learn the difference between nouns and verbs with specific phrasal structures. Okay, so the model with this very simple task will immediately learn how to distinguish the types of words that we have in languages. What else does the model learn? So models can learn facts about the world, where the capital of Denmark is not London, obviously, it's Copenhagen. Okay, so the model is learning associations between words, in this case, Denmark, capital, Copenhagen. Okay, so this is one thing that second thing that the model learns by predicting the next word multiple times. Okay, so we are talking about a corpus with trillions of words. Okay, it's trillions of words. It's all. So there's something which is the common crawl, which is a snapshot of the web. And if you go to do that on top of Wikipedia, for example, which is included in the snapshot of the web, you can learn a lot of facts about the world, and not just grammar. Other things that you learn is lexical semantics. And here we are starting to go up in the reasoning capacity of the model. If you follow this idea, you can see that, okay, some words are possible. So I went to the zoo to see giraffes, lions, and okay, spoon is grammatically correct, but it makes no sense. Okay, so there's a semantics in this sentence that calls for a noun that is part of this group. That it's part of giraffes and lions, and it's entailed by zoo. So it's something that usually happens happens together. So these words usually happen together, and it needs to be a noun. And so the model is learning lexical semantics, and so the words that make sense given the context that it's passed to the model. Okay. So the model also learns how to understand the sentiment of users or humans. In this case, if I have a sentence like this, I was engaged and on the edge of my seat the whole time. The movie was, in this case, the opinion, so the sentiment expressed in the first sentence is clearly positive, and so the movie was good. So the probability of good is higher than the probability of bad. Okay, so the model is learning a lot of things, a lot of very complex things, by simply predicting the next word. And then one of the most complex things, which we humans, we only acquire this after, I would say, I don't know, 1 year or so. So babies don't have this skill yet, which is state space reasoning. So here we have Iro went into the kitchen to make some tea. Standing next to Iro, Zook pondered his destiny. Zook left the, okay? And so here, Zook left the kitchen because this is the reasoning that the model needs to do about what or which entity is where in a given point in time. Okay, so you give the model this sequence of events, and you know where each entity is in that sequence of events, and this is a very challenging thing, a very challenging task. Something that is relatively easy is, for example, easy arithmetic, summing 2 small numbers or 3 small numbers. So the model can actually learn how to predict the output of simple arithmetics. Okay. So of course that this is something that the model learns from going through the data, but there are other things that the model cannot learn from the data. For example, it cannot learn current world knowledge. It doesn't know today's stock price of NVIDIA. This is not possible, okay? So most models have a cutoff date. For example, GPT-4, if I'm not mistaken, and even our LLM, it has a cutoff date of December 23. Okay, so the data that was provided to the model is cut off to December 2023 or some other date. It depends on the models, obviously. Okay, so what else can the model learn? So it cannot learn long arithmetic. Okay, so arbitrarily long arithmetic. This the model cannot learn how to do it. Also, it cannot learn from simple next word prediction how to solve complex math questions. Okay, so this is not feasible with just next word prediction. Something else that the model cannot learn is it cannot learn how to predict the future, obviously. Okay, so this no one can do. No one knows who will be the World Cup winner in 2038. So this is not possible. So 2038 is really distant in time, but if I ask the model to predict something for tomorrow, it will also not be able to do it. It will be just a guess, of course. And so basically, from a mathematical point of view, what we have is the next predicted token and the target losses, the target token. So we are given a sentence. So this is the probability of the sequence of words. We have the next predicted token, and we have the ground truth, and we are comparing the predicted token to the token that is actually in the sentence. And this is done at a very, very large scale. So this calculation is relatively simple from a mathematical point of view, but from an implementation point of view, it's very, very complex. Why? So first, we spend months preparing the data. We have noisy HTML, we have PDFs. This is something that takes months, that requires a lot of computer CPU hours. So in this phase, we're talking about just CPU hours, okay? We have very small GPU hours just to filter high quality texts. And this is usually done in our own computers, because it requires accessing the web, and from Mare Nostrum it's not possible to access the web, which creates an whole set of different problems. But it's obviously important to have Mare Nostrum safe, and so we don't have anything in Mare Nostrum that accesses the web, and so we do the data preparation in our own labs. Then the tokenization, which is the conversion of text into tokens, which is a code, so the entry in the vocabulary that I was showing you before. Okay, so tokenization means converting the word to the position in the vocabulary. Okay, so we have 100,000. We need to know which entry number corresponds each word in a given sentence. And so surprisingly, this takes a very long time. And so we do it, it's done once, and then we can start the actual training, because doing this during training would be too time consuming. And so the training, the language modeling training, it's done in this distributed environment of Mare Nostrum. It uses 256 GPUs per simulation. It's a gradient-based optimization. I don't know if there's someone here in the audience with this maths background, but it's the backpropagation algorithm, where we do the inference or forward pass, and then we compute the gradient, and then we do the model update. So the challenge is here is that, okay, for short samples, GPUs, so each GPU can have its entire sample, but when the samples are very, very long, for example, let's say a very long Wikipedia page or multiple Wikipedia pages, so this becomes then really difficult, because the data, so the sample does not fit into one single GPU, okay? And so we have different distribution strategies for when the samples fit in one GPU. We can have multiple GPUs with multiple samples, or when the samples don't fit into one single GPU, and then we need to distribute it across GPUs. And so we use a framework that is similar to DeepSpeed, where we have multiple GPUs, so 256, like I said, and we can shard multiple things. And in the most aggressive sharding strategy, we share also the model parameters, because the model may not fit into the memory of one single GPU. Okay, but in our case, that doesn't happen, and so we do not share the parameters. Okay, so then what follows is probably the most important training step, which is the instruction tuning. And so just to give you a perspective, so pre-training is something that has, so language modeling is something that has happened for more than 40 years, okay? This is something that has been around for many, many years. GPT-3, which was released in the middle of COVID, it only had next word prediction. Roughly 2 years later, GPT 3.5, so commonly known as ChatGPT, so it introduced instruction tuning and preference learning built on top of GPT-3 training, so the language modeling training. And what changed here was that the instructions here, the data was created manually. And manually means that, okay, we want the model not just to be able to predict the next words in a sentence, but we want the model to be useful in when the model is interacting with a human. And so the way we interact is we say something, and we wait for the other person to then reply. And so this is what was trained here. The model, the data that was used to train, which is an instruction and then the answer. This was done manually. Then more recent models like ourselves, we generate data, synthetic data. We also have data quality filters and simulation of behaviors. And so basically, so language modeling, so the first phase, it only learns how to continue sentences with the most plausible token, with the most plausible word. Okay, and GPT-3 was really amazing at doing that. It wrote even news articles for The Guardian. Okay, so that was the beginnings of this revolution. And then instruction tuning learns human communication norms, where you have a user instruction, and then you have the expected response. And the LLM is no longer just expected to complete one sentence, but it's expected to generate full sentences. So if you give the model a user instruction, you put the end of sequence. End of sequence means, okay, this the sequence of my text just ended, and then I want the model to complete after the end of sequence. Okay, and then the user instruction is passed to the model with an end of sequence token, and then the model starts to generate its own response. Okay, and this is leveraged by the knowledge that was acquired during the pre-training. And if you think about it, if you read a book in biology or I don't know, some topic that you know nothing about, and you memorize everything that is in that book, you will be able to learn or to answer questions about the content of that book. Okay, because we have this ability, and we will not be able just to complete sentences with one word. We will be able to answer requests about that book that we just memorized. And so all this data is, all this knowledge is present in the language model. And so we just need to make the model follow human communication norms, which is instruction followed by responses. And so some of the examples that were created manually and are created manually are things like this. So you have an instruction, and the instruction says, make a list of red wines that pair well with ribeyes. Use A, B, C as bullets, and then end of sequence. And then the model is asked to generate, or is expected to generate this response. A, Cabernet Sauvignon, B, Sonoma, and so on. And then when the model finishes, it puts an end of sequence. Okay. By the way, end of sequence is just a special token in the vocabulary. So it can write letters with input data. So it can follow a simple request like this one here. I need you to write a resignation letter to my boss, but then I can pass it constraints that the model should follow, which is my name, Anthony, name, AirTech, position data analyst, boss name, Albert. Okay, and then the last day. And then the model will write a resignation letter, but it will add the details that I provided in the context. Okay, and this is an important thing for when the model needs to fetch data from the web. Okay, so this is relevant. I don't have time to discuss it in this talk, but this is also quite important. So another aspect that the model needs to learn is how to extract information from very long text. So we can give this instruction to the model. Please prepare a table containing a summary of information of the participants at the conference. I have the summary of the conference, and the model can generate a table with information that is extracted from this summary. Okay. So note, this is all done at the instruction level, which is probably one of the most critical things, because it will really shape the way we perceive the user, the LLM, in terms of utility. Okay, which is how good the model is in following the instructions that I provide the model with. Okay. So it also has reasoning capabilities. For example, this is a math problem with Ariana, Danny, and Robbie, and each one has a given number of chocolates, and we need to compute how many chocolates they have. And so this is the reasoning of how the model should reach the conclusion, and the model learns how to do these calculations by learning how to predict this type of responses. And so the instruction tuning is something that is similar to the cross entropy loss, but here we have a new thing, which is we have the target tokens, we have the target response, which is the variable y, and we have the instruction tokens, so the user request, which is variable x. And in the previous equation, we didn't have that. So here we are predicting the next tokens based on the user request and all the tokens that the model has outputted so far. Okay, and that's why some of the some LLMs they output their responses in a word by word fashion. Okay, because the model is actually doing all this calculation. Okay, so we have the user request and all the conversation before, and the model is computing the y at the moment. And when we see the words coming out in the interface, what we are seeing out is the y's. Okay, so in terms of instruction tuning, again, at Mare Nostrum 5, we do the tokenization, and we do the language modeling and the instruction tuning objective, but now it's a much smaller scale, and it's 64 GPUs per simulation. We generate a lot of synthetic data that simulate certain behaviors, and this is how we train the model. So lessons that we learned from training in Mare Nostrum, it's that we should do the maximum of pre-processing before reaching the GPU. So we should also monitor GPU utilization in terms of memory, data transfer, and the number of cores. And here I'm really just showing you some simulations. So each Mare Nostrum computer has 4 GPUs. This is a machine that is similar to the ones in Mare Nostrum. And we have GPU 0, GPU 1, GPU 2, and GPU 3. And the brown line is the GPU memory, which is almost 100%, you see? But in terms of cores usage, this is actually not optimal. This is quite low. It's, I would say, roughly 50% if you look at this. Okay, so this means that most of the time the GPU is waiting for data to be transferred or to be processed. So it's waiting for CPUs. Okay, so this just means that there is probably a better way of running this simulation or calibrating the parameters of this simulation to take the most out of the Mare Nostrum GPUs. And so this could be, for example, loading the data in advance. We may not have requested enough CPU cores to read the data from disk. This is something that can happen. Or we are doing some data processing in the CPU that is slowing down the usage of the GPUs. Okay, So in Mare Nostrum, so gradient checkpointing is something important if we need to restart the simulation after some point, and this may be because the cluster is somehow not, so it may have some shutdowns. We are not fully confident that the data will not cause some out of memory problem, and because we don't want to lose some days or multiple days of several days of simulation, we can use gradient checkpointing. And in Deucalion, the memory is not as much as in Mare Nostrum, and so some of these problems end up being more frequent in clusters with GPUs with less memory. So this is really just some sharing of the lessons that we learned in doing Amália, the instruction tuning, and the final phase that follows the instruction tuning is the preference learning. Okay, and preference learning is something that has been quite on top of it has been discussed because these models are designed, they are specifically designed to be always pleasant to the user and always to agree with the user in a way. And this is called preference learning. It's called reinforcement learning. It starts with very few manual manual samples. And then it has a lot of synthetic data generation, but synthetic data generated by the model itself. And how is this done, and what is the rationale? So without going into details, because this is to be a different talk, so the model can actually give different responses to the same requests, because the decoding strategy can be a top K or a top P, and instead of selecting the most likely word, I can select the most likely next word from the top 10 most probable. Okay, and so that introduces some randomness, and the model can actually compute different responses, and all responses may be correct. Okay, all responses may be correct, but the answers may have different tones. The sentence constructions may be clearer for understanding, and so they actually have a preferred value that can be assigned by humans. Even if two answers are correct, I can say, okay, but this answer is nicer and it will be better understood by the population of users in general. Okay, and so we have this situation where you have the model generating multiple different answers, but one is preferred in respect to the other. And so what we do with the reinforcement learning and preference learning is we teach the model to reinforce its preferred behaviors and to mitigate behaviors that users do not prefer. And so this can be done with direct preference optimization. And here we have a mapping between the language model policies and the reward function. So we want a reward function that rewards the good behaviors of the model and penalizes the bad behaviors of the model. Okay, so this involves training an initial reward model with preference data, with human preference data. And this is where we have manually curated and written data by saying this sentence is better than the other sentence. So one answer is better than the other. And this way the model learns which phrasal constructions are more useful and which phrasal constructions are clearer for the user. Okay, so this is a reward model, just for example, based on the linguistic traits of the model answers. And so we have a model that can then learn how to reject data, low quality data, which do not follow this reward function. And then we can train the model with DPO. So this is not cross entropy anymore. So, but in this phase, we teach the model how to distinguish the preferred answers from the non-preferred answers. And this way, the model will learn how to just generate the preferred answers. Okay. Okay, but as the name of the family of methods say, this is reinforcement learning. So we want to reinforce the capabilities of the model, which means that we will use then one model, the LLM that we learned in the previous iteration to generate more answers. And the answers that the model then generates are passed to the reward model, and the reward model will know which answers are preferred in respect to the other. And this will just reinforce the preferred behaviors, because this loop is done a few times. Okay, this loop is done a few times, and so the model will reinforce its preferred behaviors. So this is the strategy that will deliver the final model. And reinforcement learning in Mare Nostrum 5 has a very peculiar architecture, in the sense that, or training architecture, in the sense that we have 1 to 2 inference nodes. So this is launched within Slurm. We have an LLM loaded, and here, this part here is just these models. So the models are generating data. These models generate data. Okay, so we have 1 to 2 machines, so 8 GPUs generating data. Okay, and so the model is uploaded to VLLM. I don't know if you are familiar with VLLM, which is a framework that can distribute LLMs across multiple GPUs so that inference is faster. And this will improve throughput of the sample generation process. And then the training nodes, we have 16 training nodes, which collect the examples obtained by the other nodes. We run the reward functions, and then we update the model with those examples which passed by the reward function. And then we have an orchestrator node, which is typically run in the inference node, because this is a very low cost daemon. And so it's easy to run in the inference nodes. And so this environment has been quite challenging to set up, because we have multiple environments for different rewards. We don't have just one reward function, we have multiple reward functions. I just described the linguistic reward, but we have rewards for maths, for puzzles. So there are rewards for different type of tasks. And then just to conclude, so the LLM, the core of LLM of Amália is built as I just described. So the images and speech will also be part of it. So I didn't have time in this talk to go through that. And then applications will be developed in multiple domains: education, government, culture, but this is really just applications and not the actual development of the model. And so the LLM is being created by an amazing team of linguists, data engineers, data scientists, and proof of concept developers. Then we have people from all stages of their careers. So they are master students, PhD students, researchers, engineers, professors, linguists. So they are from all kind of area and career levels. So thank you very much, and I'm happy to answer all the questions you may have.
So thank you very much for this great talk and the very nice overview of this project. Please, all of the participants, you can write your questions in the chat. If anyone wants to talk, I can unmute you individually, so just raise your hand. And while we are waiting for the questions, I would like to ask you the first question. So it is regarding the cultural and linguistic identity of Amália. How did your team ensure that Amália captures the cultural and linguistic specificities of European Portuguese compared to other variants of Portuguese?
Yeah, so that is a very good question. So most of the data is okay. So Portuguese is a widely spoken language because there's a lot of Brazilian speakers, and that means that the European Portuguese is actually in a way a low resource language because we don't have as much data for European Portuguese as for Brazilian Portuguese in general. Okay, and so this creates a challenge, and the way we solve it. So we had to get more natively written language for European Portuguese. And then a challenge was also the benchmarks. So the benchmarks has been a very challenging topic, and the linguistics the linguists they are writing benchmarks and data to assess the cultural variety of the model, and we can see that the model is actually better in European Portuguese, but we also observe that the cultural aspects are indeed quite challenging, like learning the proverbs, local knowledge, local references, which are just typical for Portuguese and not for other countries. Portugal. I mean Portugal. Okay. So this is a quite challenging task, which we have been addressing by adding data with this knowledge.
So I don't see any question, but I have one more question regarding the future use of Amália. So where do you see the most promising areas of application? Is it in public administration or education, research?
Yeah. So I think the model is quite good in specific tasks, in solving specific tasks. Okay. So the models this size, they are quite economical, and they offer a very good trade-off between operational cost and capacity for specific tasks. And that could be, for example, for education, to help users find information in the materials that the teacher or the professor provides them, answering specific questions that the answers need to be grounded on the materials that the teacher provides the classroom. It's one of the examples. Another example could be to go through, imagine a survey with data that you don't want to put it online, or you don't want to put that data in other outside your own premises, so you can run this model to do those tasks. So there are many multiple tasks which can be solved with a model like Amália. And the trade-off between operational cost and outcome and quality of the result is quite good, in my opinion.
So thank you very much. If there are not other questions, I would like to thank you, Professor Magalhães, for sharing your work and providing us such a great view into the technological and linguistic innovation behind this project. And I now see one question from Hugo Branco, so I will read it. Good morning. I hope this message finds everyone well. Congratulations on the presentation. Is there a planned date for a functional use case for this LLM? What use cases are currently planned? Thank you.
Well, so we have multiple domains. Okay, so we are working on the domains. We are providing the model with the capacities in different areas. We have some proof of concepts, some internal proof of concepts. Some are better than others. In general, we are quite happy with the use cases that we have. So we have already use cases in this domain. Internal use cases, but these are things that take time. So education for government and culture are some of the things that we are working on. But this is not up to us to decide, because we are doing the LLM. We are doing the LLM and training the LLM for specific domains. And then the way this is structured is that entities, and by entities I mean public entities or private entities, that they can decide where they will use the LLM. So we have some internal proof of concepts, because we need to test the model, the behavior of the model, and which are the bottlenecks that need to be solved. I don't know if this answers your question, but.
And we have one more question from Bernardo Malaca. Thank you for the presentation. Have you tested inference of Amália in things other than GPU? For example, using Llama CPP in a CPU, sometimes these smaller models can run there.
Yeah. So Amália is a 9 billion parameter model with 16-bit floats. Okay, this is a bit technical. With 16-bit floats, and what we've tried is to run with quantized models with 8-bit or 4-bit floats. But the performance is not so good, obviously. And so we always run it in GPU. So we did it just for proof of concept and not for measuring. I don't know if you ask about time. No, you don't ask about time. Yeah, but not anything else besides just a proof of concept.
And one more question coming from Francesco Fusco. Is there any particular reason why you chose to do pre-training from scratch rather than fine-tuning an existing model, since a foundation model might already know a lot about grammar and would need a smaller nudge to focus on European Portuguese?
Yeah. So this has been a path, right? So we've done that some years ago. It's the kind of thing that students do in classes and things like that. So we did that work before, but the challenge here is to create something that goes beyond that fine-tuning of something that was done by I don't know, Meta or Google or Alibaba or whatever, right? So because that is relatively easy, and what happens that way is that the knowledge and the expertise would always remain elsewhere, okay? And you can see that we are not the only ones, and this is something that we are all doing, and trying not to be completely dependent from non-European companies. And so we developed the knowledge. We know how to build a model from scratch. We have that knowledge now. Fine-tuning, we had that knowledge many years ago. And doing from scratch is a completely different problem. It's a completely different beast. It's much more challenging. And so now we have the knowledge and we are better in terms of innovation capacity. So just to be clear, it doesn't mean that there aren't use cases where fine-tuning should be the solution. Okay, so fine-tuning is also still valid. Okay, but here the goal was to create this capacity of doing an LLM from scratch.
So thank you very much for the explanation. On the current development of the Amália, would you be available to be contacted to test new cases? Question from Hugo Branco.
Yeah, please go ahead. Do contact me. We will see if we have bandwidth, if we have capacity. So the way we are doing it is we just not move. Sorry. So we have people that is developing the core LLM, and we have people that is working on the proof of concepts and not proof of concept, but in the domains. Okay, because the model need to be enriched with data from specific domains. Okay, it can be enriched by there we go, by fine tuning from a specific domain, or with RAG. I don't know if you know what it is, RAG, but it's retrieval augmented generation. So we get data and then we provide in the context the data that we want the model to reason about, and then the answer is computed based on the data that is retrieved from a database. Okay, and so yeah, so thank you. I look forward for your contact then.
So thank you very much also for this fruitful discussion we could have. The recording and the slides will be available soon on the NCC Slovakia website and the YouTube channel. We will also send out a short feedback form after the session, and I will also include the slides from the Professor Magalhães. So if you want to enter in contact with him, feel free. Please take 2 minutes to reply to our feedback form because your input helps us improve future webinars. If you would like to stay updated on upcoming events, including the next webinar in this series, AI-driven archaeology with LLMs, on 18th of November next week, please follow NCC Slovakia and NCC Portugal online. So have a great day and see you at our next event.
Thank you. Bye-bye.
Bye-bye.